In this video, we're going to talk a bit about unit vectors. If we're dealing with a vector v of length 1, we call that a unit vector. We have standard horizontal or x, y, and z unit vectors. So I is the x unit vector. It is 1 unit in the direction of x. J is the y unit vector, 1 unit in the direction of y. And k is my z unit vector, 1 unit in the direction of z. So if I have any vector with an x, y, and z component, we can write this as a linear combination of these 3 standard unit vectors. So here we have our proof. V being that vector v1, v2, v3, x, y, and z in component form. I have 1 v1, I have 1 v2, and 1 v3. So I've essentially unadded here, right? I've split this up, I've added in a bunch of zeros, and adding zeros is the, identity property of addition, so it doesn't change anything at all. So I've split it up so I have a 1x and a 0 for y and z, 1y, a 0 for x and z, and 1z, a 0 for x and y. In each of those 3 situations, I can factor that component in front of each of these unit vectors. So v1 times the unit vector 1, 0, 0, v2 times the unit vector 0, 1, 0, v3 times the unit vector 0, 0, 1. And so since these 3 component vectors represent the standard unit vectors, I've got v1 times I, my x component, v2 times j, my y component, and v3 times k, my z component. Let me pull in a picture. So what we can see here is we have some resultant vector from p1 to p2. And that resultant vector was initially the sum of 2 vectors, O to P sub 1 and O to P sub 2. Now, each of these original vectors that we summed can be broken down into their standard unit vector components and be written as this linear combination. So there's a specific to achieve each of these points, there's a specific quantity of x movement, y movement, and z movement to get to this end point. So we have a certain quantity of x's, a certain quantity of y's, and a certain quantity of z's, again, to get to that end point. And we can think about these as the x, y, and z components, or the I, j, and k components. So any vector, regardless of whether or not it is one of the 2 initially summed vectors or the resultant, can be written as these I, j, and k components. Looking at what we have here, I've rewritten this, or I've got this rewritten here as this resultant, the sum of those 2 vectors, as just being the difference of your x's, the difference of your horizontal components times I, the difference of your y components times j, and your z components times k. So everything that we've talked about in the previous videos still applies. And as long as the vector we're dealing with is not the 0 vector, then it has a length of magnitude, which is also not 0. So we start coming to this process of developing a unit vector. And a unit vector is a vector of length 1 in the same direction as the non-zero vector v that we are considering. So if we take that vector v and divide it by the magnitude of the vector, that is going to give us a vector of length 1. And this is the derivation, I guess, for it. But the main thing here is the vector divided by the magnitude of the vector gives us a unit vector. That gives us a vector in the same direction as the original vector, just of length 1. So reiterating what I just said, as long as our vector that we are considering is not the 0 vector, then v divided by its magnitude is the unit vector, and it's in the same direction, but it's a shorter length. It is of length 1. A unit vector is length 1. And this equation right here, v times the magnitude of v times the unit vector, v over its magnitude, which is balanced. If you think about crossing that out, that would just be v equal to v. This expresses v as its length times its direction. Let's find a unit vector u in the direction of the vector from p sub 1 to p sub 2. So these are 2 points. So the first thing we need to know is what is our vector that we're dealing with. So let's determine v in component form. V is the vector from p sub 1 to p sub 2. And in component form, that would be 3 minus 1, 2 minus 0, and 0 minus 1. So I'm just subtracting each of my x, y, and z components. So this gives me that my vector v equals 2, 2, negative 1. Or rather, v equals 2i plus 2j minus k. Now, if we want the magnitude of the vector, magnitude of this vector is going to be the square root of 2 squared plus 2 squared plus negative 1 squared, or the square root of 9, which is 3. So my unit vector, my vector of length 1, which represents 1 unit of my vector v from p sub 1 to p sub 2, my unit vector, bold u, is equal to bold v divided by the magnitude of v, or 2i plus 2j minus 1k over 3. So my unit vector u is 2/3 I plus 2/3 j minus 1/3 k. So this represents a unit vector in the direction of my original vector from p sub 1 to p sub 2. This vector is of length 1. And I can check that by finding the magnitude, right? The magnitude of u would be the square root of 2/3 squared plus 2/3 squared. And then we've got plus negative 1/3 squared, which is, of course, the square root of 4/9 plus 4/9 plus 1/9, or 9/9, which is the square root of 1, or 1. We have one more example in this video. If v equals 3i minus 4j represents a velocity vector, if we want to express v as a product of its speed and direction of motion, well, what we said is that v is equal to its magnitude times its unit vector. So in order for us to solve this, we need to first determine the magnitude and then the unit vector. Well, the magnitude of v is the square root of the squares, or the sum of the squares of the components. So I've got 3 squared plus negative 4 squared, which is the square root of 9 plus 16, square root of 25, which equals 5. And my unit vector is that vector divided by its magnitude, right? The unit vector. So that would be 3i minus 4j divided by the magnitude, which we just found is 5. So my unit vector is 3/5 I minus 4/5 j. So taking v, remember v equals 3i minus 4j as given when we started the problem, we can now say, well, v is the same as 5, the magnitude, times the unit vector, 3/5 I minus 4/5 j. So 5 of those unit vectors will make a vector of magnitude 5, which represents the original vector. I have one more video I'm going to do in this series where we do some application.